Last thing I did before I left my office, another email the entire department. Now,
I hope so. Yeah.
I can walk over there if you want me to. Because I sent him up a practice phone, but I just don't
Okay. Coffee's here. Yeah, it's live streaming.
So if I stood up and
Please don't.
made up some gestures in front of you.
I was wondering.
I was
I just stood up.
Well, this entire conversation is being picked up by the mic. What? Okay, yeah. What? Yep. Thank you.
You knew my boss is going to be late, right?
Yes.
Okay. You had this experience.
There's so much going on. So I don't like the amount of cost. Background business.
Liz, how are you doing? How are you doing, Liz?
It's very nice.
Thank you.
Are you sure you're on this level? No, I like the black one, but it's got spots on, so it's not completely stiff. Excellent for this. Airbrush is good. You're about to become a doctor, we can't abuse you anymore, so we have to. You're fine, it's David.
Ohio State. So the university. The Ohio.
It's David. You graduated last year. You just put an extra year in with this skill. Right?
Hmm?
You got a lot last year, right?
thank you all for coming. I'm glad you chose this room. It's quite a crowd. You must have done something. So today David is going to defend his thesis.
Watch the Watch the coin.
The title you can read faster than I can say. It's a very interesting subject. It's an interaction between electronic and phonon states in the system. David came to us from Ohio State after finishing his BS in physics and chemistry. So today he's going to defend his thesis. You're free to ask questions, but you can wait until the end of the defense. Then we come to. Okay? So I'll let him. Oh, he's been working with Dr. Lioi for the last 2 years. Sorry, Gaurav.
All right, thank you for the introduction. Hello, everybody. My name is David Lioi, and today I'll be presenting symmetry breaking in the correlated electronic and lattice degrees of freedom in the copper-doped TX phase diagram, titanium diselenide TX phase diagram. And so I'm going to unpack that title as we go along, but the first thing I want to talk to you about is symmetry. So an object is symmetric if there is a transformation over which the same object is returned. So take a sphere, a three-dimensional sphere. If I rotate it around these three principal axes, I'll get the same object back. However, if I deform it, like you see here, if I break the symmetry, then two of these, I can no longer do this rotation the same way. I have to do integer multiples of 180 degrees. Whereas this rotation, I can still do continuously rotate it around to get the same object back. If I bring this back to a sphere and then break the symmetry again, so now I've broken it even further, and so this rotation I have to do every multiples of 72 degrees. Now, if I bring this object back to a sphere again and break the symmetry in a manner reminiscent of thermal noise, then it's going to look something like this, where I can no longer rotate this object to get the same object back. I can no longer do any of these rotations. The symmetry is very broken in the system, and by that I mean at a specific time and not time averaged. Okay, so this is important because of this statement right here. The symmetry of a system implies degeneracy of energy states and vice versa. Now in this context, degeneracy of energy states just means that the energy states are the same energy. So you have two objects, the energies are the same. And so energy in a quantum mechanical sense is that you have an object and it has a phase and it oscillates back and forth, and the rate of this oscillation is what determines the energy. So you have positive and negative, whereas if you have another object and it oscillates faster, then this is going to be a different energy object. Now, their symmetry breaking on a quantum mechanical level is called symmetrization. So you take two highly symmetric objects with the same energy, you combine them, and you create a new wave function out of that, so that with a broken symmetry from before. So say if I bring two objects together, they have the same energy, so they're oscillating back and forth the same speed, then they can either be in phase or out of phase, like I've shown you here. So if they're in phase, then they're going to constructively interfere, and if they're out of phase, they're going to destructively interfere. And you're going to create new wave functions from this. And so the bonding orbital, or the lower energy state, is going to be a broken symmetry from what you had before, and the anti-bonding orbital is also going to be broken, but it's going to be at a higher energy. Okay, so with this you can create all of your macroscopic systems. So in this case, we're going to take an atom, and this is an energy momentum diagram, where momentum is the oscillation of the wave function in space. So that's when you see the dispersion, that's what that is. And so if I bring these objects together, I get these new states, and bring more objects together, I get these new states, where this state right here is the one that's they're all in phase with each other. So this is a very important point in the band diagram, and this is called the gamma symmetry point. And so if I look at this energy state, that's what the wave function look like, and in between. And I can keep playing this game, I can keep putting atoms together, and I can create what we call an electronic band diagram. Now I can do this in one dimension, like I've shown you here, 2 dimensions, 3 dimensions to create 3-dimensional crystal lattices. But I can also use more than this wave function. So this is just the 1s wave function, so it's just like a hydrogen atom. But there are other atoms in the periodic table. They have more wave functions that electrons occupy. And so you can create much more complicated band diagrams, an example of which is shown here. So this is titanium diselenide, where this is the highest occupied electronic orbital, as they would say in chemistry, or the Fermi energy, as we would say in condensed matter physics. And so these lines that you see here are calculated from the tight binding model. where you consider only the nearest neighbor interactions. You only consider a single electron approximation, whereby you don't consider, you'll have one electron in a lattice of nuclear sites that are all positively charged, and you don't consider any electron-electron correlations. Okay, so if you make that, so if you make a construct or calculate the band structure for a material, and so you get something like this, you can also have something called correlations. And so correlations in a material, so any material with internal correlations are called correlated materials, and correlations are any degrees of freedom whereby, so say you had all these states that made up, so say this was a state, a wave function here, there's a wave function here, and these are orthogonal under the tight binding approximation. But if you allow these other correlated degrees of freedom, then they're no longer orthogonal, and you can get symmetry breaking through those. You can get additional symmetrization. So these can include deformations of the lattice, so phonon scattering of electrons from one band to the next. You can also have Coulomb interactions, and you can also have magnetic coupling. And so, an example of what happens when this coupling happens, if you lower the temperature of a system, then you can get symmetry breaking through one of these correlated degrees of freedom. And so what you start with is some high temperature state, and where you have thermal noise, which breaks the symmetry like so. And then if you remove the thermal noise such that you allow the energy states to become degenerate with each other, they will then form through those correlated mechanisms that I mentioned before, a new symmetry breaking. There's a new symmetrization of the wave functions, which changes the macroscopic symmetry of the system itself. And so, right here is an example of a correlated material phase diagram. So in the vertical axis is temperature, and the horizontal axis, in this case, is charge concentration. So in general, what you'll be seeing these phase diagrams a lot. And these black lines represent the thermal phase transitions, which is what I just showed you previously. So this is another thermal phase transition into the superconducting state. And these black dots right here represent the quantum phase transition. So a quantum phase transition is if I cross into a new phase while going in the horizontal axis, a thermal phase transition if I cross phase transition going in the vertical direction. Okay, so an example of a material that's somewhat similar to, or that's another correlated material, is in the pnictide class. So this is barium, iron, arsenic, where this horizontal axis is cobalt concentration, and this is temperature. So this is a phase transition into a spin density wave system, where you have the spins of a spin wave modulation in the lattice of the system. And if you suppress this transition temperature, you get a superconducting dome, what is called a superconducting dome. And here are thermal fluctuations of this phase above the transition temperature. Another example is the transition metal dichalcogenide. So this is tantalum disulfide. This horizontal axis is now pressure, but this is again still temperature. So this is just another X value. And again, you can see suppression of this, in this case, a charge density wave system, and then you also get a superconducting dome in the phase diagram as well. So the system that I will be presenting today is going to be titanium diselenide doped with copper. And so the doping with copper gets me the horizontal axis. And in this case, what I'm